All right, welcome to this explainer. Today, we're basically going to put on our biology professor hats to approach machine intelligence from a totally different angle. We're going to explore the biological wetware that directly inspires the machine learning systems that are quite literally changing our world right now. I really want you to think about this for a second. How does the incredibly complex biological machinery of your own mind serve as the exact structural blueprint for artificial neural networks? As we dig into this today, you're going to see that AI isn't just some random assortment of cold algorithms. It's actually a profound mathematical reflection of the very cells firing inside your head at this exact moment. Section 1, the biological blueprint. Let's dive right in. Let's start our journey by looking right under the microscope, zooming all the way down to the cellular level. There is a direct one-to-one structural comparison here that is just fascinating. In the human brain, the fundamental unit is the biological neuron, which receives chemical signals through its branching dendrites. In an artificial neural network, the digital equivalent of that basic brain cell is called a node. Just as those dendrites catch chemicals, this digital node receives incoming numerical values, which we call vectors, from the layer right before it. But here's a really crucial detail. A biological neuron doesn't just indiscriminately react to every minor stimulus it gets, right? It relies on synaptic strength, and that strength increases through repeated experiences and feedback. The more a connection is used, the stronger the signal it passes on. And this brilliantly illustrates how the digital equivalent, called a weight, functions in an artificial node. Digital weights mimic this exact biological process by amplifying important numerical signals and kind of dampening the weak ones. It basically determines the importance of the input to decide if the node should react at all. So the artificial node calculates a weighted sum of all those incoming numbers. But to make a final decision, it needs one more piece of the puzzle: bias. This is simply an added numerical value that shifts a node's weighted sum up or down. Think of it as a sort of baseline inclination that finalizes the decision. It sets up the threshold logic for whether that signal continues on its journey or just stops dead in its tracks. And what determines that threshold? Well, that's the activation function. You can think of these mathematical formulas with funky names like ReLU or sigmoid as the ultimate digital trigger. We can compare this directly to the biological limit required for a physical neuron to actually fire. In biology, if the total electrical charge in a cell body exceeds a specific limit, boom, it fires an electrical impulse down the axon. That's the action potential. The activation function is that exact same limit. It decides if the mathematical information is important enough to pass on to the next link in the chain. Moving on to Section 2, layers of digital perception. Now, when we zoom out from a single cell, we see that intelligence doesn't just happen in isolation, it completely emerges from interconnectivity. Let's walk through this step-by-step path of information. Step 1 is the input layer. Think of this exactly like human eyes receiving raw light data from the environment. Step 2 takes us deep into the hidden layers. These are the real processing centers. Just like your brain's visual cortex identifies basic edges before recognizing complex shapes, these hidden layers mathematically process features to identify increasingly complex patterns. And finally, step 3 is the output layer, which takes all of that heavy processing and triggers a final classification, like, say, confidently recognizing that the image you're looking at is a cat. All right, Section 3, learning through guided practice. You see, a network doesn't instantly know what a cat looks like. It has to learn it. In biology, this is governed by Hebbian theory. Neurons that fire together wire together. Our digital networks mimic this beautifully through a process called backpropagation, which honestly perfectly mirrors practicing a skill to improve performance. Let's break down the steps. Step 1, the network takes a guess. Step 2, a mathematical equation called a loss function measures the mistake. Step 3, backpropagation kicks in. The network sends that error signal backward through its layers, adjusting the weights of every single connection to reduce errors over time. It is literally just like shooting a basketball, analyzing why you missed and tweaking your grip and posture backward through your muscles to optimize for your very next shot. I want to pause on step 2 for a moment because it's so important. The loss function mathematically calculates the exact difference between the network's prediction and the actual truth. You can relate this directly to how our own brains learn from making mistakes. It's the mathematical equivalent of the biological pain of an error. When you mess up, that negative feedback tells your brain to optimize its neural pathways so you don't do it again. While the loss function provides that exact same critical feedback loop for the machine. So the really crucial takeaway here is this absolutely stunning one-to-one mapping. Digital software completely mirrors biological wetware. Look at this. the biological neuron becomes the digital node. Dendrites map perfectly to input vectors. Synaptic strength is replicated by weights. The threshold of an action potential is mirrored by the activation function. The signal transmission down an axon becomes the output link. And finally, the biological miracle of synaptic plasticity is recreated right there through backpropagation. It is just a breathtaking architectural mirror. Which brings us to our final takeaway. A neural network is not just a black box of math. It is a structural mimicry of the most complex machine in the known universe. I want to leave you with this provocative thought today. As we watch artificial intelligence become more and more incredibly advanced, solving problems through connection and reinforcement rather than rigid code, we aren't just looking at clever math. We are, in so many ways, looking in a mirror. How close to actual biological intuition can this digital wetware truly get? Thank you so much for exploring this fascinating connection with me today.